coming back. Really appreciate it. It's my ego. So last time we was very close to we built up a lot of machinery and we were very close to getting a bunch of consequences. So last time, what was the machinery we built up was that if you have a circularly ordered group, which is from now on going to be a group with a 2 cocycle. And we had some sketch that showed that this was equivalent to being circularly ordered in terms of that map C, which takes in 3 elements. So if you had a circularly ordered group, you could build a left-ordered central extension, right? G tilde F, where F is the circular ordering, and it comes with a cofinal central element. And the point is that you can this correspondence between the cofinal central element runs through the correspondence between H2 and central extensions. So now let's do some consequences. This is going to be fun. Well, all definitions of fun. Okay. So proposition. G, a finite CO group. G is cyclic. I promised that I would prove this. Here we go. We can prove it not too bad now. It doesn't take too much work. We do have to rely on a group theory fact of Stallings in the 70s. Not too bad. So what we're going to do is we have a finite group here. So we're going to look at this group here. So consider the LO central extension 1 to Z to G tilde to G to 1, corresponding to some circular ordering. I don't really care what the circular ordering is. And G tilde is torsion free because it's left orderable. Right. LO implies torsion free.
It's virtually.
G tilde, so G is finite, so G tilde has a finite index subgroup, which is Z. So G tilde is virtually cyclic. That's called being virtually cyclic. If you haven't seen virtually before, virtually just means it's a finite index subgroup that satisfies something. Okay, so G tilde is virtually cyclic. And so by a result of Stallings, this is usually stated as torsion-free virtually cyclic equals cyclic. This means that G tilde is cyclic. Hence, G is cyclic. Great. That's fun. Okay, so if you have a virtually cyclic torsion-free group, is that your cyclic? Let's prove some more corollaries following from this machinery we have. Proposition. So let's suppose that you have some group GF is circularly ordered. Circularly ordered such that F is 0 in H2. Okay, so suppose you have a circular ordering where the cohomology class of the circular order is 0. Then G is LO. It's actually left orderable as well as being circularly ordered. And here's the proof. We run back to this correspondence again.
The direct sum active.
Yeah. And then we remember that if this is 0, this is the group in the middle is just Z cross G. This is the proof. Consider this 1 to Z to G tilde F to G to 1. But since F is the trivial cohomology class, F equals 0, in H2, Z, we have that G F tilde is isomorphic to Z cross G. G tilde F is left orderable. That means G is left orderable. G is a subgroup. Right. And G is L. Now that these things just come out for free. It's very satisfying when you do a bunch of irritating work and then you get something for it. It's not always the case, right?
Being both LO and CO give you something strong.
Is being both LO and CO. I mean, that's the same as just being LO, right? Because left orderable implies circularly orderable.
You also see it from the co-cycle, like the fact that it's always zero maybe means that you don't ever wrap completely around the circle or something.
No, that's not good enough. So Z, H2 of Z with Z coefficients is trivial. But there are circular orderings which wrap around. So every circular ordering has zero as its cohomology class. But there are circular, I mean, you're leading towards what I'm going to start talking about soon, which you call secret left orders. And then we're going to talk about bounded cohomology. Then you'll get refinements of. Okay, so here's a corollary. Suppose that you have a group is such that H2 of G coefficients is trivial, like that, for example. Then G is LO if and only if G is CO. Cool, eh? So in particular, you know, you might have a integer homology 3-sphere. And then if you can show that pi1 of that X is circularly orderable, you immediately have as left orderable. If you're interested in showing that 3 manifold groups are left orderable. Some big conjecture or something. Right. Why does this follow? It's exactly because of that. If you have a circular, so left orderable implies circularly orderable. We showed that already. If you have a circular ordering, it has to be zero in cohomology. So by the previous proposition, left orderable. Okay, here is a fun one, which is rather surprising, if you ask me. I'm sorry, are there any, before I do this one, just a little more involved, are there any questions about the first couple of propositions I wrote? Okay. But if it looks like I'm high, it's because I have allergies. Let's get that out of the way now.
That does not say that every circular order is a left order.
No, it does not say that. It just says there exists, right? This is an existence. G is left orderable. It doesn't mean that the circular ordering you started with was secretly left order. Correct. Sorry, Jacqueline. Right. So G, a circularly orderable group. Let's take that as our assumption. And F, a finite normal subgroup. A finite normal subgroup. Then F is central. I have a note here to leave it as an exercise, but I think I'm going to at least sketch out why it's true. This isn't obvious by any means of the imagination. So let's have a proof sketch. Okay. What's the idea? You restrict your central extension to F. So when you unwrap F, you've got some sort of central extension of F, which you know is Z. Okay, so okay, yeah, let's just go it. Okay, let's consider, let me write the short exact sequence here. So 1 to Z to iota to G tilde to G 1. And then over here, I'm going to split the short exact sequence off to F tilde to F to 1. Okay, and this is also iota, but just restricted. So F's living inside G, and I just want to consider this central extension coming from restricting the circular ordering down to F. This is Z, right? F tilde is Z. So let F tilde be generated by some element A. It's a copy of Z. Now, then pi A is equal to pi of A tilde. I didn't write down what pi was. Here's pi. I'm going to abuse notation and call that map the same thing. And this generates.
Sorry, so F tilde should be generated by A tilde?
Nope. Oh, yeah. Yeah. No, that's exactly right. Thank you. This generates F. F is a finite group, it's cyclic. So I've picked the generator of Z over here, and then that has to generate what's down here. Right. Furthermore, and A to the N is equal to the identity. Because it's a finite group. So it's a finite cyclic group, there's some order of the finite cyclic group. Thus, A tilde to the power of N is in iota of Z. It's something that maps to trivially here has to be in the image of iota. So it's central. So how did I write this? There's like a slick way to write this out. All right, so A tilde N central in G tilde. Now let G be in G tilde. A to the N tilde is equal to G A tilde to the N G inverse because it's central. Nothing's happened to it. But I can call this G A tilde G inverse to the power of N. This equality is happening inside the integers, inside a group which is Z. Z has unique roots. So this implies that A tilde is equal to G A tilde G inverse, which implies that A is equal to pi of G A pi of G inverse. And that's good enough. Because every element down here in G is of the form pi of G for some.
Wait, why do we know that the elements are in iota of Z? You just know that the powers are in.
Yeah, because we know that A to the N goes to the, is equal to the identity. So what's that saying? That's saying that pi of A tilde to the N is the identity. So you've got something here which maps to the identity here, so it has to be the inclusion.
The Z that we're in is F tilde,
Correct.
and F tilde is normal.
Correct.
So G A tilde G inverse is also in F tilde. That's what we use.
Oh, sorry. Yes, there is a gap there. Oh, sorry, I misunderstood your question. Yeah, that's right. So how do we, this has to live inside Z? So this is central, so we know that's there. But then over here, yeah, sorry, this is an element of Z, exactly. Right, so you've got two roots inside Z of A tilde to the N. They have to be equal.
Z being F tilde. Yeah.
And the Z being F tilde. Thank you. So we have the following corollary. Any group of the form Z mod NZ with a non-trivial semi-direct product. Any group that looks like this. So a non-trivial semi-direct product. Product is not CO. So there are some two knot groups which have this structure. I don't know exactly which ones. I was asked whether a certain two knot group was circularly orderable and it had this kind of structure, so you can prove immediately that it's not circularly orderable. Even though it might have the property that every finite subgroup is cyclic, it's fine. You can show that it's not circularly orderable. This is pretty powerful. Having this left-ordered central extension. Something you can now do using what Adam showed you in lecture 1 or 2. He showed you that every countable left-orderable group embeds into homeo plus R. Here's an exercise. G countable. Then G is circularly orderable if and only if G embeds the homeo plus of S1. you can now prove this. Yes.
I have a question. I don't see why A tilde over n, if A tilde over n equals to that conjugation over n, this implies that A tilde is equal. Yeah, that,
So
I don't understand.
the point is that you've got two elements. You've got two elements in the, this is all, this and this is all taking place inside F tilde, which is isomorphic to Z. Because it's a central extension of a finite group, which is tangent free. Right, so this is isomorphic to Z, the integers. And in the integers, if you have two elements which power to be the same thing, they are the same. Their nth powers are equal, then they are equal. This is exercise, this is true in general for bi-orderable groups. They have unique roots. Yeah.
Sorry, a really silly question. So you deduce that the generator A is invariant under conjugation. Why does this imply that the subgroup F is central?
So A generates the subgroup.
Yes.
And this is showing that if I conjugate by any element in my group G, it doesn't change the generator.
So it's in the center.
So it's in the center, right? So then the whole group has to be inside the center.
So the power of two integers are equal. One might be the negative of the other.
That's true. I'm going to pick this to be positive.
It's a bi-orderable. No.
No, sorry, that can't be true. Sorry.
Cyclic group, not in
Not
C.
a cyclic group, no.
Okay.
Positive power, the same
Yeah.
power.
It's the same, yeah. No, sorry, you're right. Thanks. I think Riley's here. All right. All right, great. Any questions about this?
Which virtually free groups are circular?
Which virtually free groups are circularly ordered?
That's not a question you have to answer.
Yeah, I'm not going to. But
Those which are free by finite cyclic.
we might find a cyclic.
Only those?
Only those, yes. And exactly those. Any free by finite cyclic.
Okay. So let's talk about this question of which circular orders are actually circular orders and not just secretly left orders. Okay, because we know in the integers, right, you can take a left ordering on the integers and that's secretly a circular ordering is what we did in the first lecture. So let's talk about secret left orders. And we know that the integers admits uncountably many circular orderings. So some of them are not just left orderings. Let's try to identify them. All right, so definition. Let's talk about what we mean by a secret left ordering first. So a circular ordering. C on G. Yeah, I'm going to define it in terms of C. So it is a secret left order. Secret left ordering of G if graveyard and chalk up here. Okay. Right, I'll do it. So if there exists a total ordering, a left ordering this on G. I wish there was a way to pronounce that symbol. It would really make life easier. So if there's a left ordering that gives you the circular ordering, that on G such that G1 less than G2 less than G3 implies that C of G1, G2, G3 equals 1. Okay, this is the definition of being a secret left ordering. It's a circular ordering that comes from a left ordering. We want to identify these somehow. Okay, so first let's investigate sort of secret left orderings a little bit more, and then we're going to introduce bounded cohomology. And that's going to allow us to identify these secret left orderings.
So a secret left ordering is a circular ordering coming from a left ordering.
Correct.
Okay.
Secretly.
Secretly in that sense. Okay. That makes sense. I like it.
Thank you. Good, okay.
I wouldn't have invented a word.
I don't know if this was invented. Do we invent this?
Oh, you made up the word secret.
Oh, great.
No, but it's great. I mean, it makes
So-
sense.
People have talked about these in other word contexts. So let this be a circularly ordered group. Any left ordering this on G such that G1 less than G2 less than G3. Let's C of G1. G2. So what this proposition is I'm just trying to write down what the positive cone of a secret left ordering looks like in terms of the circular ordering. Okay. So if you have a left ordering that gives you the circular ordering you started with, has positive cone, which is equal to the set of all G in G, such that C of G inverse identity G equals 1. This is maybe not terribly surprising if I draw the picture. But what I want to get at is that this proposition tells us if you have a secret left ordering, there is a unique left ordering that gives you that secret left ordering because a positive cone is determined. So in particular, there is a unique, right, that's how I want to write it. There is a unique left ordering, yes, inducing a secret left ordering. Again, I'm not going to prove this. It's not terribly difficult to prove, but let's just draw the picture. Okay. So here's my secret left ordering as a circular ordering. There's the identity. Okay. As a circular ordering. So if I take something in the positive cone, which is all the stuff to the right here, G, this is where G inverse has to live because it's a left ordering. This exactly says that the positive cone is G inverse identity G is mapped to 1. Where are you going?
I don't understand what one should prove there. Like once you can pinpoint the positive code.
Yeah, that's what you should prove.
Positive cone tells you the order. I don't understand.
No, that's exactly right. I just want you to write proves that this is the positive cone of the left ordering.
Oh, okay.
I mean, the picture makes it seem very plausible
Yeah,
and even suggests a proof.
Yeah.
That's why I'm not going to prove it. Yeah. Obvious things are sometimes false, though, right? So you should prove them. Yeah. In saying that, I'm not going to. Okay, so in order to talk about secret left orderings, the natural place to look to find them is a place called bounded cohomology. So I'm going to introduce that now. Bounded cohomology is a very good name because it tells you exactly what it is. Cohomology, where all your cocycles and co-boundaries are bounded. Let me write that down. Precisely, so bounded cohomology. I really enjoy names in mathematics where the name suggests what's true. Hard to remember who's attached to which property. It's much easier to just name the property. So we're going to look at the set of bounded cocycles, right? So what is this? These are all the functions, the cocycles in Z. Oh, sorry, I have to give you a group and the coefficients here of G and Z. So this is all the elements of regular old Z such that F is bounded. Okay, what do I mean by bounded here? Is this is a map to Z. So it means there's some uniform maximum, some uniform upper bound for all the values that this particular function can take. There's not a uniform upper bound over all functions. Functions could get arbitrarily big, but each function itself is bounded. So this only makes sense when you have coefficients which are ordered, where there's some notion of a bound, right? This doesn't make sense if you change these coefficients to Z mod n. And the same for the cocycles, co-boundaries. of G Z is the set of all F in B2 G such that F is bounded. This is kind of strange the first time you see it. I didn't like it when I first saw it. Amazingly, and yeah, just I think amazingly, it tells you a lot about. Well, we're going to see. It tells you a lot about whether or not something's a secret left ordering, and then you can even extract more information, some more dynamical information about things called rotation numbers and things like this from the bounded cohomology. Really quite amazing. Okay, here's the first thing to notice. A circular ordering on G defines a bounded cohomology class. Simply because the definition of a circular ordering is that it's a cocycle. One of the conditions is that it takes values in 0 and 1. That's bounded, very bounded. Cool. So now let's ask, what can we say? What can we say about a circular ordering, knowing what its cohomology class is? It's bounded cohomology classes. So here's the first thing I want to prove for you. So let G, F be a circularly ordered group. If F is a secret left ordering, if it's a secret left ordering, then F is 0 in bounded cohomology. Let's just prove this thing. So if there is a, oh, sorry, there's one thing I want to point out here. I'm stating this in terms of F, right, 2 cocycles, but the definition of a secret left ordering was given in terms of C. So you have to move between those two, that correspondence between C's and F's here. And this is why people ask, this is sort of, why don't you go straight to cohomology in terms of C? Is because this theorem is not true. It's true up to mod 2 considerations, but it's not true. So the F's are the right things to look at.
Shouldn't this also be true in usual cohomology as well?
No, because
Yeah.
so the integers, every circular ordering on the integers is 0 in regular cohomology. But there are circular orderings on the integers by just mapping the generator to an irrational rotation in S1, circular orderings which aren't secret left orderings. It's not going to be true.
So you mean the second bounded cohomology of G equal to integers, it's not trivial.
Yes, in fact, it's S1. It's like uncountable. It's isomorphic to the group S1. It's big. Uncountable is. Yeah. Okay. Let's prove this. At least I'm gonna hide some details, but we get the general idea. So let P be the positive cone of the secret left ordering. Okay, what do we have to do to actually show that this thing's trivial? We have to show that F is actually a boundary, right? So there's some function which F is equal to like D of A plus D of B minus D of AB, right? There's some cocycle condition you have to, sorry, there's some co-boundary condition you have to show that F satisfies. So we're going to define a bounded function B from your group Z as follows. Okay. B of G is 0 if G is in the positive cone or the identity, and it's 1, I guess, if G is in the inverse of the positive cone. This is a perfectly good bounded function. Bounded, it maps to Z. And then we check that F of GH is equal to D of G plus D of H minus D of GH. All right, this is what you have to check to show that this is actually trivial in bounded cohomology. It's equal to a coboundary. Here's how the proof goes. We split it up into cases. I'll just do one case. So if G, I'll do a couple of cases. This one's silly. If G equals the identity and H equals the identity, then what happens, right? So the left side 0, this is 0, this is 0, this is 0. So we're good. Great. And I won't even write it down. Okay, you just check from the definitions of what we've got there. Okay, let's do a case which is a little more interesting. So if G equals H inverse, then G is not the identity. Then we know from the definition of F is that F of GH equals 1, because this is one of the conditions of being a circular order. Here it equals 1, so that's the left-hand side. And for the right-hand side, right. For the right-hand side, we have that D of G plus D of G inverse minus D of GG inverse. One of these is in the positive cone, one of these is not. So exactly one of these turns out to be 1. This is always 0. So this equals 1. So this case is good to go. And you just run through every case, right? G is positive and H is negative, blah, blah. You run through and you show it works. So exercise, do the rest. Questions about this?
Yeah. So you said that for the integers, the bounded cohomology is the circle. And is every cohomology class realized by a circular order?
I suspect the rational rotations are not.
So before you were describing some circular orderings, so how was that? You map.
I pick the generator of the, I choose a generator of the integers, map it to an irrational rotation.
Okay.
That circular ordering corresponds to that.
Oh, I see. And
To that cohomology class, bounded cohomology.
so you're saying, and okay, and the cohomology class associated to this ordering is said the rational.
Correct.
Said the irrational. No, like, yeah, said the irrational angle, say. And oh, I see. And then you're saying maybe the other guys are not realized. And then, but then the other question is, how do?
Oh no, they are realized lexicographically. Sorry, they are realized. Everything's realized. I take it back.
The rational.
The rational rotations are also realized by circular orderings that look like coming from Z goes to Z goes to Z mod K goes to 1. There's a lexicographic circular ordering you can put on this. So on the circle, it's sort of the elements here rotate by 2 pi on K.
Okay.
And the elements here, they don't rotate.
Okay.
So they just squish and push some stuff around.
And this realizes like, sorry, rational angle.
Yes.
So, but then, okay, then the other question is, I suppose, how do different circular orderings with the same bounded cohomology class differ?
Yeah. So
Do we know that?
we do, but now like, I mean, we could just do the rest of the course.
Oh,
yeah.
Sure, I'm. Yeah.
It's about rotation numbers. So you could say something about rotation numbers, whatever they are.
Okay.
In terms of circular orderings, you can sort of define a rotation number of an element intrinsically. Two circular orderings with the same bounded cohomology class will give you the same rotation numbers on every element. So I think there's a natural question to this when I write down a lemma like that. It's like, what about the converse? Where you would like this to be a complete characterization. At least I would, and it turns out to be true. So lemma, one time. Could be better. Let GF be a circularly ordered group of the converse, right? So if F is 0 in bounded cohomology, and F or equivalently the circular ordering corresponding the map from triples corresponding to F is a secret left order. This lemma gives you a complete characterization of when orders are secret left orders. when circular order is a secret left order. Just look at bounded cohomology. All right, let's see what I can leave out of this. So I'll try to sketch this without too much effort. So suppose, without too many details, so suppose that you have f of gh is equal to d of g minus d of h, sorry, plus d of h minus d of g of h. Okay, and both these functions are bounded. In particular, d is bounded. Okay, so step one is you first show that d of g has to be in 0 and 1, has to take values in 0 and 1. So assuming that d is bounded, you can show that this has to happen. Let me try to sketch this thing out. I'll do one direction, one step, sorry. So suppose that d of g is less than or equal to -1. And suppose, oh, actually, you know what? I'm gonna hint towards kind of an inductive argument. I'm going to show that d squared has to be less than or equal to -2, and then show that d cubed has to be less than or equal to -3 as a consequence of this. And then this will show that d was unbounded, so this can't happen. Okay, so then we know, let's see what the trick is. What have I written down here? It's just nonsense. Let's just have a look. So f of d and g, this is equal to d of g. Oh yeah, no, this is fine. Whew, that was close. D of g minus d of g squared. Okay. This lives inside 0 and 1. Left-hand side lives inside 0 and 1. So I have this is bigger than or equal to 0. And then this is less than or equal to -1. This is less than or equal to -1. In order for this to become positive again, so this is less than or equal to, so this here is less than or equal to -1. This is less than or equal to -1. And this implies that this value here has to be less than or equal to -2. And then you play the game again with g and g squared to show that d of g cubed has to be less than or equal to -3. So d is unbounded, so ... So d is unbounded, which can't happen. And similarly, you make a different set of arguments to show that d of g can't be bigger than 2, bigger than or equal to 2. D of g cannot be bigger than or equal to 2. That's a different set of tricks that you use. And now, once you know that d of g, so you know that d of g lives inside 0 and 1, and now you use this to define the positive cone. Now let P be equal to all the g's such that d of g is equal to 0 without the identity. So it's actually a positive cone. And then you check, you unwrap the definitions of F's and C's, and you check that this gives you a positive cone for F. So it's a secret left ordering. So this gives the positive cone. Sketchy proof for sure, but that's the general construction. But the take-home message for this right now is that bounded cohomology is telling us something more about the structure of the particular circular ordering. In particular, if it's trivial, you can identify when or not, whether it's in particular, knowing whether or not it's trivial in bounded cohomology tells you whether or not it's secretly left ordering. This is kind of neat. Gives you lots of information. Let's try to extract some more information. Okay, Adam actually hinted at this today. We're going to define rotation numbers by first moving to the central extension, defining translation numbers there, and then taking that mod 1. And that's going to give us a number between 0 and 1, which is a rotation number of an element. Let GF be a circularly ordered group. Define the translation number of an element in the lift. Find the translation number So we're going to pick an element in the left ordered lift and talk about the translation number of that first. All right, so here's how we define it. The translation number with respect to the circular ordering F of an element NA is equal to the limit as k tends towards infinity, 1 on k, times this thing, which I'll tell you what it is in a sec. Respect to F. Draw a picture out. So this is a floor function. This is the way you should think about it. It's a floor function. So where the floor of some element is just equal to m. And remember, so where's this coming from? Here's a picture of your left ordered central extension G tilde. Here's the identity. And here's the point 1, comma identity. Here's the point 2, comma identity. So if you have a point in here, let's say, it looks like 2, comma A for some A. So the floor of it is just going to be 2. It's sort of, if you think of this as a real line, the floor of a real number is just the integer just below it. And then you can define the rotation number by taking the translation number mod 1. For A and G, find the translation number. Sorry, rotation number. That's what I wanted to find. Of A, rotation number of A as rotation number with respect to some circular ordering of A to be equal to the translation number of NA mod Z. So you pick a lift, you look at its translation number, you take that number mod Z. There's a bunch of things which should make you nervous here. One of them is that I've taken a limit. If you're a well-trained first-year calculus student, does it exist? Adam already gave a hint as to why this exists. There's some argument in terms of saying that this sequence is subadditive or something very close to that sequence is subadditive. So by the lemma Adam wrote down, the limit exists. And also, this should be independent of your choice of, this should be independent of your choice of A. So exercise, show this definition is well defined. Definition is well defined.
Why do you put? Oh, because it's we want to look only at the first coordinate for the floor function.
So you're asking why did I put the F there? Because it depends, like the whole this group, yeah, it depends on F, right? To construct the multiplication. Yeah. That's why I put F. It's all with respect to the circular ordering I've picked. Yeah. So then you can define the rotation number. You lift up, look at the translation. Okay. So I'm going to write down a couple of exercises and then I'll stop. Just to get a good bit of intuition for this. So exercises. So show that the rotation number of e to the I theta in S1 is theta, where maybe you normalize up to 2 pi, depending on your conventions, but morally it's that. Again, you do certain examples to check that the definition is the right name you've given to the thing. This is one of them. Here's another exercise. This is a fun one. Show that if F is a secret left ordering, F is a secret left ordering on G, then the rotation number with respect to F of G is equal to 0 for all G. It should be true morally, right? If you're secretly left ordering, there's no wrapping around a circle going on. And not only is it true morally, it's true. Which is great. Okay, I better stop there. Because I'm hungry.
Is there a converse of the second exercise that if you know that the rotation is 0 for each, if you have an F and the rotation is 0 for each G, is it
0 in bounded cohomology? Is that your question?
Yes.
Yeah. What? It's not true, right? Yeah.
In ping pong, Schottky ping pong.
Okay.
Any element is 2 fixed points.
Sorry.
Intro-
Answer.
Okay, take F2. Acting in the standard ping pong the Schottky ping pong. So any element is hyperbolic in PSL2 of R. And so any element has a fixed point. So its rotation number is 0. The action is an action on the circle of which
Which has no.
no global fixed point.
Okay. So the answer is no. I mean, there is an exercise and it's of that example.
Yeah, thank you, thank you.
Yeah, just to translate. So it's just so I understand. So like there's an example where every element acts by rotation number 0. But the whole group does not act with the global fixed point. So it's bounded cohomology class is not, so it's not secretly a left ordering. Yeah, okay. Great. Good to know.
There's an F class group with probably by similar.
When you could say
Maybe not everything. Explain.
about that after, yeah.
I noticed you didn't specify the circular ordering on S1 in this exercise at the top of the board there.
I did not. I'm going to specify it by saying, take the standard left ordering on R, then quotient by the subgroup of Z generated by the element 1. That's a central cofinal element. So when you quotient, you get a circular ordering on S1. That's a circular ordering you should use.
Are there others? You know, like on R,
Yeah.
how you can make all these bad leftovers. Sorry to put you on the spot. I don't.
Do you know the answer to this, or are you
I'm
just,
not.
you're just testing me?
No, it's not a test. I don't actually know what.
Yeah, I mean, this is an interesting question. I was talking about this yesterday. You have a standard circular ordering of S1 or a standard, you have a way of constructing left orders at homeo plus R equivalently. Are there exotic ways to do this? I would expect the answer is no.
This is
S1.
just S1, so
Yeah.
I think that you may be only one, but I don't think.
You should know there's only one left, the circular ordering on S1, right? No, I think there are other things you can do.
So there are many left orders on the reason.
There are many left orders, but
So
you want the cofinal central element.
many ways to order the group of homeomorphisms that we align.
Yeah.
Because if you do the lexicographic trick, at each moment you can prescribe whether you go to the right or to the left.
Right.
Yeah.
Okay.
So you get some temper explosion of the. And even doing that, you don't get all the orders in the group.
Oh, okay. Yeah, you've got an answer to your question.
Yeah.
Andre has an answer.
Yeah.
This is an answer to your question. Yeah, but circular orderings on S1. I mean, what's the instinct here? The instinct is that this is the only one, right? No, you think you should have other ones.
Yeah. It should be doable. You know, whenever you have some S1 acting on the circle, you have to prove that the action is continuous and it is indeed the action by rotations.
Oh, okay.
Because you don't have for free that the action of S1 on the circle is the one by rotation. Because what is that? It's like you have the rationals and then you have the irrationals. So you have a free part and then there is the Q part. So on Q, maybe you know what it's doing, but on the free torsion free part, you can do whatever you want. Because there's an abstract group, it's not nice.
Like, I think we know that there's only one circular set.
Yeah, we know there's
Yeah.
one on the screen.
Yeah,
so if you
that's
just-
why I asked about S1.
Yeah, and then you have all the rationals and then you can do whatever you want.
So could it be that the homeoblasts are somehow solves the classification problem in the sense that if you have like if you have a countable group and it maps in homeoblasts R, then it's orderable because you can just restrict one order from there. Is it possible that all orders on the group are obtained by restricting orders from homeoblast R?
I mean, this is.
I don't, yeah.
But that was the way I didn't understand.
Because the embedding you get is an order preserving embedding. And then, I mean, you get an embedding into homeo plus R in an order preserving way. So that exactly means that you've got that's a restriction of a left ordering on R.
Okay.
Homeo plus R, sorry, homeo plus R, yeah.
So, but there can be multiple orders restricting to the same order.
Yeah, and you can have groups where they embed in homeo plus R, and some of their orders come from restricting orderings on homeo plus R, and some don't. But then you have to have, they have to be not countable or something like this in order for something bad like that to happen.
Yeah, in the realm of countable.
Wait.